In the last class, we have studied about the basic concept of optical fiber, including the total internal reflection and the different regions of an optical fiber and different types of optical fibers, step index and graded index fiber, single mode and multi-mode fiber, and the different modes of propagation of an optical fiber, and also the acceptance angle. Here once again I am explaining the acceptance angle for preparing your notes. Here a step index fiber is shown in the figure. Let mu1 be the refractive index of the core region and mu2 be the refractive index of the cladding region, and the mu1 will be greater than mu2 to satisfy the condition for total internal reflection. Here the incident ray, it makes an angle theta I with the optical fiber, and the refracted ray is theta r, and this refracted ray, it makes an angle at the core cladding boundary, and this angle is phi. And if this angle of incidence at the core cladding region phi is greater than the critical angle phi c, then only the ray undergo total internal reflection at the interface. If the angle phi will be less than phi c, then the light ray will go out of this core region. Let mu0 be the refractive index of the air medium surrounding the optical fiber. And here we can apply the Snell's law. From the Snell's law, at the face of the fiber, the refractive index of the fiber medium, that is the core medium, divided by the refractive index of the mere medium is equal to sine of the angle of incidence to the sine of angle of refraction. That is mu1 by mu0 is equal to sine theta I divided by sine theta r. And this equation is considered as equation 1. If the value of angle of incidence is increased beyond a limit, then the angle of incidence at the core cladding region, it will drop below the critical value phi c. Then the ray will escape from the core region. And to undergo and to keep the total internal reflection condition, we are considering that the largest value of the angle of incidence at the air fiber region, that is theta I, it occurs when the phi is equal to at least phi c. From the triangle ABC in the figure, sin theta r is equal to sin 90 minus phi, or sin 90 minus phi can be written as cos phi. And the equation 1, we are substituting the value of sin theta r as cos phi. Then the equation 1 becomes mu1 by mu0 is equal to sin theta I by cos phi. When phi is equal to phi c, theta I will be theta maximum. That is mu1 by mu0 is equal to sin theta max divided by cos phi c. But from the conditions of total internal reflection, we have the relation mu2 by mu1 is equal to sin phi c. Therefore, cos phi c is equal to root of 1 minus sin square phi c. Sin phi c is mu2 by mu1. Therefore, sin square phi c is mu2 by mu1 the whole square. Therefore, cos phi c can be written as root of mu1 square minus mu2 square divided by square root of mu1 square minus mu2 square divided by mu1. That is, mu1 by mu0 is equal to sin theta max into mu1 divided by root of mu1 square minus mu2 square. Therefore, sin theta maximum is equal to root of mu1 square minus mu2 square divided by mu0. If the rays coming from the air to the fiber medium, then the refractive index of the air mu0 is 1. Therefore, the sine theta maximum is equal to root of mu1 square minus mu2 square, or theta maximum is equal to sine inverse mu1 square minus mu2 square. The angle theta maxima is called the acceptance angle of the fiber. Thus, the acceptance angle is the maximum angle that a light ray can have related to the axis of the fiber and propagate down the fiber. Light incident at an angle beyond the theta maximum, it refracts through the cladding and the corresponding optical energy is lost. If larger be the diameter of the core, then larger will be the acceptance angle. And this is an expression for the acceptance angle, that is the acceptance angle theta maximum is equal to sine inverse mu1 square minus mu2 square. And from this acceptance angle, we are explaining another term called numerical aperture. Numerical aperture we are explaining here. What is numerical aperture? The main function of an optical fiber is to accept and transmit light from the source. The light gathering ability of the optical fiber, it depends on the core size and the numerical aperture. Thus, the numerical aperture, it determines the light gathering ability of the fiber. And this numerical aperture can be defined as the sine of the acceptance angle. That is, numerical aperture is equal to sine theta max is equal to root of mu1 square minus mu2 square. That is, numerical aperture is equal to root of mu1 square minus mu2 square. The numerical aperture, it depends on the refractive indices of the core and the cladding region. And this equation, we can mathematically rearrange this expression for the numerical aperture. That is mu1 square minus mu2 square. And this equation is like a square minus b square. A square minus b square is a plus b into a minus b. Similarly, mu1 square minus mu2 square is equal to mu1 plus mu2 into mu1 minus mu2. And we are multiplying and dividing this equation with 2 mu1. The both numerator and denominator are multiplying with the term 2 mu1. And then we are approximating the equation. That is, we are approximating mu1 plus mu2 by 2 as mu1. That is, we are approximating that mu1 is equal to mu2. When mu1 is equal to mu2, mu1 plus mu2 divided by 2 is equal to 2 mu1 by 2. The 2 will cancel and it will be mu1. That is, we are approximating mu1 is equal to mu2 in the equation, and then mu1 plus mu2 by 2 can be written as mu1. And the remaining term we are taking mu1 minus mu2 divided by mu1. It is denoted as a delta. That is, mu1 minus mu2 divided by mu1 is taken as delta, where delta is the fractional refractive index change. Delta is the fractional refractive index change. Then substituting these two values in the above equation, that is mu1 square minus mu2 square is equal to mu1 into delta into 2 mu1. It will be 2 mu1 square delta. Therefore, the expression for the numerical aperture is equal to root of mu1 square minus mu2 square. That is root of 2 mu1 square delta, or numerical aperture can be written as numerical aperture is equal to mu1 into square root of 2 delta, where delta is the fractional refractive index change and mu1 is the refractive index of the core. Thus, numerical aperture is a measure of the amount of light that can be accepted by a fiber. Its value ranges from 0.13 to 0.5. A larger value of numerical aperture implies that a fiber will accept a large amount of light from the source.